So thank you for being here. All of you, is great for me being here. I, like Anthony Valentini, am a little bit the minority here, as it was obvious from the vote we took a little bit before. So I will try to address all of you thinking of the previous vote, which was an overwhelming vote in favor of many words. But there was also many of you who didn't know what to answer the vote. So I'm addressing also those people in particular young people here. And I will try to talk the relational view and present it, assuming that you know little about it. Otherwise, there would have been many more hands going up for it. First of all, of course, this Oxford here is, the gang of the many world, the hideout of the many world people. But also the relational view is the new arrival on the new kid on the block in the panoramic, in the landscape of ways of thinking about quantum mechanics. So I assume to many of you this is going to be new, even if there's a lot of in common with other views. And in fact, there's a lot of in common with what Max was telling before me. We found remarkably few things we disagree. So I'm also trying to convince Max that he's inside a relationalist without him knowing, and help you to discover the relationalist inside yourself. The first lecture today will be basically on foundations of quantum mechanics and cosmology. So it's the title of the series here. I'll focus on that. There's no quantum gravity, no gravity. Tomorrow I will bring gravity in, and you will see that with gravity some of the strange things about the relational view simplify much. So hold until tomorrow before your final judgment. And also that I believe the relational view is a clean way, is the only one I know, to make sense of quantum gravity, to apply quantum gravity to the universe, to the early universe. And I will end up by showing you some, presenting to you very shortly, because that's not the main theme, some of the applications of loop quantum gravity to early universe. So I will arrive at the end to some possible quantum gravity effects with all the possible quotes around in the cosmic background, possibility for computing these things, not because I want to show those calculations, but I want to argue that there is a point of view of quantum mechanics where you can do that easily, simply, without having to climb mirrors so much. So let me start from the first by trying to bring clarity to something I believe it's a source of confusion. I think this is a common source of confusion. I think that progress in physics and in philosophy comes from clear ideas. So let me try to disentangle one thing. So let me start very easy. Suppose I have an harmonic oscillator, okay, something that oscillates. I can describe it, and this is the equation, the classical equation that describes it. You know how to write the quantum formalism for describing it, and this is all, we all know how to do that. Suppose I have the solar system. Then so the Newtonian physics is not enough, relativistic physics, you have nice equations. People study the solar system, people study the galaxy and have equations that describe well or bad the dynamics of the galaxies, maybe there is dark matter and so on and so forth. And there are other people who study the universe, and they call themselves cosmologists, and that's what is cosmology, that's what cosmology means in today's science. Now, what are the equations here? Well, there is a Friedmann equation. This is a version of it. There are some perturbations. We're describing the perturbations. Why am I saying these totally obvious things? Because this is a harmonic oscillator. Is that equation describing everything here? Obviously not, right? Inside here, there is a lot of stuff. There are probably bacteria moving around, having their love stories, whatever they happen. There is atoms with quarks, with gluons. Okay. If I describe as a harmonic oscillator a molecule, which is a great success in quantum atomic physics, a molecule is perfectly harmonic oscillator. Some molecules, right? And it works perfectly well quantum mechanics, ignoring that inside the molecule there are atoms, inside the atom there are nuclei, inside that nuclei there are protons and neutrons inside there are gluons and quarks, and who knows what else, we don't know. Inside maybe nothing, maybe something. So what is the point I'm making? That in each of these cases we're not describing everything that goes on in the system. We're describing some degrees of freedom of the system. Are we doing this sort of randomly just because we like? No, because when I describe the motion of this, what I'm looking at, what I'm caring at, the way this is affecting me is in this amplitude, nothing else, okay? The way it hits me, the way the photons. So I'm describing the way this object affects me with an appropriate equation. And this is also true down here. You'll say, well, wait a moment, I'm not just describing the scale factor when I do cosmology. I describe the perturbations. The perturbations include everything. Do they include everything? This is what we measure, right? And in fact, the L here, or the K here, goes all the way to 1500. It's a big number, right? 1500. So if you multiply by the polarization, whatever, a few thousand. So what are we describing in cosmology? We are describing the Hubble radius, roughly, divided by a few thousand, which is a million light years. So, like when I do the harmonic oscillator, I'm sort of neglecting the love stories of the bacteria. When I do cosmology, I'm neglecting everything at a scale below that a million light years. Okay? Why? Because that's what cosmology, by definition of the cosmologists, that's what the cosmologists do. Okay? So the fact is that cosmology is not about everything. Physical cosmology, when people talk about physical cosmology, they're talking about much less than everything. They're talking about a few degrees of freedom, a few thousand degrees of freedom, which are few compared to all the ones of the world, which are defined by taking the large scale and making a mode expansion and just cutting out the high modes and just sticking to the short mode. So one disregards the short wavelengths, where short millions means a million light years. Everything that happened from the beginning of humanity to now is just not seen in this approximation here. Now, you can say, okay, sure, but Simon, I can hear him immediately say, sure, but I'm interested in doing the quantum theory of everything, not just of these few large degrees of freedom. This is perfectly legitimate, and in fact, I think it's a very interesting question, but it deserves a name, and it cannot take the name cosmology, which is a name which is already taken in science, to mean something else. So I've looked for a name. I've gone all sort of everythingology, allology, and then from the Greek allos, allology, panology, omniology, tautology. First, one could use metaphysics, quantum metaphysics, but that's bad because it comes with a sort of, and then the physicists would dislike it. So finally, I came out with tautology as the less ugly one, from tautos. Tautos means. Oh, I didn't think about that. Let's call it tautology. Totos is Latin, right? Everything. I mean, if you're Italian, you should know Latin. So the point I'm making is that tautology is legitimate, but don't confuse tautology and cosmology. The two things have nothing to do with one another. One thing is the study. You can change the name, but there's one thing which is a study of large degrees of freedom of the universe. Is what when you show these big pictures of everything, right? It's everything. It's not everything. It's a large. And the other thing is tautology. Okay. So when Joe Silk started this meeting yesterday by saying this is the universe. Okay. Of course, this is the universe, but careful, because universe, the word universe might mean different things. It might mean this, or it might mean the totality of existing things. This is just a teeny fraction of the degrees of freedom of the universe, just large scale ones. Okay? From this confusion, I believe, from mixing up two senses of the word universe, universe has two distinct meanings, I think it comes an enormous amount of confusion. Tautology is a legitimate enterprise in people interested in foundation of quantum mechanics, but has nothing to do with what happened to the large scale of the universe. Nothing. Okay? And let me insist a little bit what are the differences between the two problems. If you do quantum cosmology or even classical cosmology, you obviously have to do with gravity, because that's the dominant force out there. And if gravity is in, means that space-time is dynamics. So you have questions like space-time is just made by one connected region or many. There are many universes, but not many universes in the sense that there are many times everything. Many universes, many different disconnected parts. Or an infinite universe, there are questions like you don't have a Schrödinger equation, you have a Wheeler-DeWitt equation, which means an absence of a preferred time variable, and so on and so forth. These are all questions that come out when you do cosmology or quantum cosmology or foundation of cosmology, which has nothing to do with considering all the degrees of freedom, because you're just studying those degrees of freedom that have this property in their characteristic. Tautology would be a problem that existed even if there was no gravity. No inflation, no expansion of the universe, no problem about Big Bang. It would just be, can we do quantum mechanics of everything without the observer? I'll come to the observer in a moment. So in the problem of quantum topology, can we ask questions like, what are the interactions between what is the observer of the totality? Okay, but again, do not confuse large with the whole. So one of the questions that Joe mentioned at the beginning is, who is observer? In quantum mechanics, we learned quantum mechanics from the fathers of the 20s, the 30s, who were thinking in terms of a system and apparatus that measure it. Okay? So we have this notion of observer, to which I will come back. Who is observer in cosmology? Well, I mean, that's completely easy. It's us, our telescope, the Planck spacecraft, all the stuff here, which are all a little bit smaller than 1 million light years. So they are not part of the system observed. They are not some of the degrees of freedom studied in the equations that describe cosmology, right? This will be important later. Now you will say, but we are in the universe. Of course, but we are in the electromagnetic field. And when I study the electromagnetic field in this room, the long wavelength, I'm not disturbed by the fact that I'm in, or that some atoms might be sensitive to it. I cleanly take the electromagnetic field, I do a Fourier expansion, I consider large degrees of freedom, I'm something else, which is interact with it. In the universe, I do a mode expansion, I have the large degrees of freedom, I can consider the scale factor, I consider the large fluctuations, and I'm something else. I'm something small that looks at that, take data, and interact with this. Okay? In tautology, it's a completely different story, because by definition there is no observer. If the observer is something external, there is only internal observer. So I close this initial part. Do not confuse the specific features of the dynamics of large-scale degrees of freedom, namely the universe in the sense of physical cosmology, with the problem raised by trying to understand what is quantum mechanics of the whole. These are independent problems, and very simply, do not confuse large with whole. This is a children confusion, so let's not do it. Good, so this was about setting what we're talking about. I will talk about both, right? Cosmology and tautology. I'm not saying that one is stupid and one is intelligent, not at all. I just want to separate issues. Now let me come to relational quantum mechanics, and this will play a role on. Again, I assume that you don't know anything, so I'll start slowly. These are some. It started long ago in the late 90s, but nobody paid attention to it. Then there were a number of papers. Now there are a lot of papers in the subject. Some philosophers get interested. Bitbol, who is a Kantian in Paris, Michel Bitbol is well known in France, and Van Frassen, who I think all you know in Princeton. This doesn't mean Bitbol is a Kantian, Van Frassen is an extreme empiricist, I would say. I'm also mentioning to distantiate from the philosopher's reading of this thing here. I mean, I'm not a Kantian, I'm not an extreme empiricist, I consider myself a realist. So I'm talking about interpretation of quantum mechanics, not philosophy, not metaphysics, which is not my. So what's the core point? The core point is very simple, and let me go back to the beginning of quantum mechanics. Quantum mechanics was born in 25, and then Schrödinger wrote the Schrödinger equation in 26 in two different manners, right? Heisenberg wrote a table of numbers, and Schrödinger wrote a wave in space. I think, and that will be the main theme, that Heisenberg had it a more useful intuition, that it's more useful to keep understanding the world. And Schrödinger success, the intuition of Schrödinger had a success because it was more similar to classical physics, but it's misleading us. That's a starting point. Of course, Schrödinger was thinking of wave in space, and as you know, very rapidly, Heisenberg, I think, was the first to realize that this makes no sense, because as soon as you have two particles, the wave, Schrödinger wave, is not in space anymore. So the waving configuration space is Schrödinger sort of intuition of quantum mechanics. Tables of numbers are Heisenberg intuition of quantum mechanics. What was Heisenberg thinking? He has a nice story in which he tells how he got to the idea. So let me repeat to you, unless you all know it, how Heisenberg's story, how he got to the idea. So he says that he was in Copenhagen, and he used to, think about that, and go out in the night and walk in the park. And the park was dark, and the only thing that he could see is some lamps here and there, and there's some islands of light here and there. And one day he sees a man. I don't know if you can see the man here, okay? There's a man under one, just walking, okay? And a moment after, the man is not there anymore. Oops. And then he sees the man here, okay? And then disappears again. And then he sees and so on, so disappears then. And then he thinks, well, there's nothing mysterious about that. A man is a heavy, fat bunch of flesh and, stuff, which are not things that appear and disappear. They keep, so it should be somewhere in between. So I know that I know where he is. I can fill up the dots in between. And then he gets a flash. Yes, a man is a big fat, but what about an electron? An electron is not a big fat thing of flesh. Maybe for an electron it doesn't make sense to filling things up. Maybe an electron, I don't need to say, to know, to talk. There is no meaning to where he is. Maybe an electron is something that manifests itself here and there when it interacts with something else. I'll come back to that, of course. That's his initial intuition, okay? So the description of reality that Heisenberg has in mind is not something that increases on the ontology of classical mechanics. It's not more, it's less. There is less in the ontology. So Heisenberg's intuition was take the ontology of classical mechanics and take away stuff and leave a sort of minimum, and that's maybe enough for describing the world and for saying what is the world as far as we know. When do I see the man? When it interacts with me, when the photons coming to him come to me. So maybe the best description of reality is in the way things affect one another. So let me declare, like Max did, my basic assumption. I fully agree with realism in the way Max presented it. External realities hypothesis. So facts happen, and they happen in Andromeda also when I'm not looking at them. The universe is there, it's nothing to do with my existence and not my existence. Okay? I profoundly agree with all his beautiful rhetorical speech about no spatial role in humans. He put it as no secret sauce hypothesis. I fully agree. I'm made of atoms, maybe not just atoms, also electromagnetic field, but the stuff, the standard stuff of physics are made of atoms, and everybody else is, and that's sufficient. That has to be sufficient for understanding things. That's my assumption. Maybe I'll change idea the day in which somebody will bring evidence for that, but the fact that there are things we still don't understand doesn't mean that this shouldn't work. So I don't think there is special role to humans, no to macro world, no to records, no to anything like that. I mean, the world is made by a simple physical system that interact with one another. And especially, I agree with Simon, beautiful speech, rhetorical speech, which I share 100%, that we should not have our philosophy imposed on our physics. It's the way around. I'm not a philosopher, so I don't want to talk about philosophy. I want to talk about intuition. I think that physics has gone ahead when reading out of what we've learned about the world, we have adapted our intuition to what is out there, and not, never in the history of physics, to my knowledge, a step ahead has been made by taking our intuition and forcing it on something that didn't seem to work nicely and simply. So I fully agree with this starting point. Let's try to say what works in physics and how we can adapt our intuition for that. But I want to be realist about what Heisenberg was a realist about and what comes to be completely natural to be realist about. Real physics is about facts. Facts that happen. The electron is here and hits me here. This is here. This is black. You're looking at me. The table is, the cup is on the table. So technically, the phase space is where points, where things are, and that's what happens in physics. That's what's real in physics. So if somebody is looking at some system, he make a measurement or whatever interacts with this, and in the moment of the interaction there is something that happens, the spin is up. I think that the spin is up, period. Okay? There is a fact, let me call A this fact. A value has a certain, a quantity, a variable has a certain value, a spin has a value plus 1/2, and so on and so forth. Come back to this picture in a moment. I don't think physics pushes us, and here I think we are in full agreement in thinking in terms of objects. Is strongly pushing us thinking in terms of processes. Processes, what happens, and what happens at the interaction. I think is a remarkable feature of physics that so the world is a big process happening, but we can split it in different manners. And there is something magic in the structure of quantum mechanics as we have it, that the tensorial structure of quantum mechanics is magically flexible on the way you split it. You can cut the space in different manners, and it keeps being consistent. I'll come back to this point. So I think we can think of the world in terms of processes, things that happen, arbitrarily splitting it in processes, large or small. Interactions, when there are interactions between different processes or different systems, in between things happen. So sometimes they happen, sometimes they don't happen. And a state is a way of coding what has happened during an interaction. Okay, so what is the wave function? Okay, because so far we have heard about states and the wave function. Now, I think, and this is a point of disagreement, and this is what I'm sort of bringing here, is that exaggerating and giving ontological weight to the wave function doesn't help us, misleads us. A good way of making sense of a quantity, Pache-Kuhn perhaps, is to take a theory and take a limit of the theory, the previous theory we understand well, and see what it was there. If you want to know what is the mass in the Schrödinger equation, you just take the classical limit and say, that's the mass of the particle, which I knew before, right? So what is a wave function? We'll take the classical limit. In the classical limit, it has this form here, where this is a Hamilton function for small h. And if you plug this here, it's a Schrödinger function, this is a Hamilton-Jacobi function. So the Hamilton function is a solution of Hamilton-Jacobi function with some initial condition. Now, nobody would dream in classical mechanics to endow the Hamilton function with ontological weight, right? The Hamilton function is a way for computing where the particle goes. It's not the thing. It's like the Lagrangian. The Lagrangian doesn't exist in quantum mechanics. It's a law that tells us how things move. It's not the thing that exists, right? So I think the wave function can be thought and is much usefully thought as like the Hamilton function, a computational device, not a real object. And I'll see what computational device it is. So it's time to address directly what I'm unhappy with the many world. Not because I want to talk much about that, I want to talk the relational theory, but just to say where the difference is. And maybe this is a key point. I am Everettian. So Everett published this fantastic paper in I forgot the date, sorry. 57, thank you, I was 1 year old. And when I didn't read it at the time, I read it later and I was amazed by it, okay? But somehow what I read into it, and other people read into it, is not exactly what many world people read into it. The notion that I think introduces Everett there is that of relative state. Okay, what is a relative state? Well, it's very simple. A relative state is, in fact, maybe understanding what is a relative state is the key of the entire story. If I make a measurement, this is a system. I have an apparatus and measure the system. I can attribute a wave function to the system, of course, okay, as we always do. But we know from Wigner, from a lot of stories, that in fact I could also attribute a wave function to the system and the apparatus. I can move the boundary a little bit, okay? So which one is the right state? Probably the one that include this one also, but why is more right? So maybe I want to include also me, a lot of stuff. But is that what we do in the laboratory? In the laboratory, we always use the state of the system. We don't care about the apparatus, right? If you want, in many world interpretation, we use, in many world language, we use always the state, which is a relative state in the branch where I am, okay? So Simon put a wonderful criterion down, which is do justice to the practice of physics, what people do in the laboratory or what people do in quantum cosmology. Every single wave function which is written in quantum cosmology or in the laboratory of nuclear physics is a relative wave function. It's never the total wave function. You were saying no. Or almost never. Okay, maybe, maybe, okay? So the thing we talk about when we do quantum mechanics is always is Everett relative wave function, not. And how do we get it? We interact with the system, we prepare the system. We interact with the system, we write down what is its property, and we read from the past interactions the property of the system, and then we attribute a state on the basis of that. So concretely in a lab, a state is a coding of past interaction with the system and has nothing to do with this total wave function of the universe, of everything, of the tautology that in many worlds seem to play a role in the interpretation of quantum mechanics. I'm going to get to that a little bit more. So I am an Everettian, but I think that focusing on Everett relative state is much more insightful than focusing on all his... Let me be more precise here. This guy is interacting with the system, is seeing spin up, okay? So this is the wave function that he's using. There is a system was in a combination of a red state and a blue state, and there's you write the interaction, here is interact, he uses this wave function here, okay? Now he knows that if there was a bigger guy who is looking at everything, maybe there is a big wave function here, and he's just living in one of the two branches here. Which one is living here? He's living in this branch here. But he never cares about that. That's not the point, okay? In laboratories, we use this wave function, not that wave function. Second point, Max said, and maybe you will disagree with that, follow the math. Let's try as much as possible to read the interpretation out of the mathematics. Now, I think, you think, Max, you probably didn't think much when you answered the question I posed at the end of your talk, because I said, well, what is the relevant mathematics? And you said just the Hamiltonian and the Hilbert space. I don't think this is a possible answer, because you can have systems which are physically completely different, which have the same Hamiltonian in the sense in which a Hamiltonian and a Hilbert space defines something. Because given a Hamiltonian, not all Hamiltonians are equivalents, of course, but you can change basis, and the only invariant thing is the spectrum. So if you have the spectrum, which is multiplicity, it's not sufficient for characterizing a system. If you have a free particle or a potential with a bump, the spectrum does not change and the multiplicity does not change.
I disagree with that if you take the spectrum of the whole Hamiltonian of everything, but let's say that for coffee. Okay,
so I think that at least if you take a finite piece of the universe and a non-relativistic Hamiltonian, you can have physically different systems, things that we call differently with the same spectrum, I mean equivalent up to. Even worse in quantum gravity, because there the Hamiltonian is zero. So I think that when I hear things like that, in reality there are other structures which are going in. It's not just maybe the split of the Hilbert space in subsystem, maybe some observable, maybe something else, some phase space which is there. And this extra structure is crucial. I think that quantum mechanics is not just a Hamiltonian evolution, a unitary evolution in phase space with a spectrum of Hamiltonian. It's more than that. In fact, when I studied quantum mechanics, in the text there's more than that. There is some observable algebra, which is crucial, and it's not just Hamiltonian, it's the way the Hamiltonian interact with observable algebra. And the observables tell me what are possible interaction, or how I interact with a system. So I think that extra structure is needed, and Simon recognized that there is extra structure. In fact, he said explicitly there should be extra structure. There should be extra structure, and he said if we could, given the wave function and this extra structure, deduce from that, read the state as a superposition of different classical histories of the world, then the story would hold completely. I don't think we're still there yet in the many world, and I think there's always something missing. I mean, I read David's book. I try to. Every time a story is given, let's say that a card is like that, but this is adding extra structure. So this extra structure has to come out, and that's what I want to. Now, where is the origin of the confusion? I think the origin of the confusion is a simple fact about probabilities, which should jump to your eyes, which is that less information can need more numbers to express it. Right? If you have a distribution probability, P1, Pn, the amount of information is given by this formula here, which I'm not going back, I mean, Max talked about that, it's the entropy. The maximum information distributions are the one where all the P are zeros except for one, and I can indicate one of them just by saying who is X. So one number, one integer number is sufficient to give me more information than any real numbers. Easy, okay? So the wave function has more numbers, but has less information than a point in the phase space. It's fact, okay? And there was a theorem, I don't know how to pronounce his name, the Pbr Theorem, a couple of years ago, that was sort of advertised as a proof that the wave function is real. And the theorem is very good. I think it's very nice. What the theorem proves is that if you believe in hidden variables, then your hidden variables should be as rich to include the wave function. That's what the theorem is. But I think this doesn't prove the reality of the wave function. It shows that hidden variables is an implausible way of looking at quantum mechanics. It's exactly the opposite, the conclusion of the... So the theorem is very interesting, but... So the core of the story is that this is not quantum mechanics. This is just a little piece of quantum mechanics. Quantum mechanics, next to it, has operators, spectra, a set of spectra of some special operators. There's no way of doing anything in the laboratory from that. You need a set of operator and a spectra. And if you just think that you can take everything out from quantum mechanics, I think you're... let me skip Bruno De Finetti. She's one of my heroes. Now, there was a rhetorical strong move from Simon in support of taking wave function as real, which is to show the wave function, a picture of the wave function of the... This is wonderful. Of course, the descriptive role of the wave function cannot be denied, right? The orbitals, chemistry is just based on descriptive roles of where the wave function is different from zero, is significantly different from zero. But careful, going from descriptive power of something in some special cases to the ontology is a big jump, is a huge jump. Here is an example. Let me prove you that the caloric is real. Here's a picture of the caloric, right? It's a picture of heat. So heat is a substance. This is an infrared picture of... so when the heater goes on, this becomes red, you see it. You see the heat. Therefore, there is a substance in the world which is heat. No, okay? Heat is a good thing, but it's not the best way we have for describing reality. So I think that a realist who is putting his weight on the quantum state, his ontology on the quantum state is perhaps barking at the wrong tree. A question which logic people always ask is, why don't we see superpositions? I have an immense respect for Roger Penrose, one of my heroes, but I think it's a silly question. I studied quantum mechanics, and no way in my quantum mechanics textbook was written that we see superposition, because we don't see the state, right? We see element of the spectra of the observables. I can see the particle, the position of the particle here, there, or there, or exclusive, or a value of the momentum. And I never see a wave. Wave is something which I construct for doing a calculation. So if you take the facts as the starting point, what is a wave function? Well, it's easy. You interact a certain number of times with the system, there are a certain number of facts. The wave function is a way of coding the past interactions. If you know the past interactions, you can compute the probability distribution of future, because that's what physics is about, that's what science is about, that's what nature is about. What happens later can be deduced to some extent from what happened earlier. So from the past interactions, you can compute the future. Now, when I told Max that he's a relationalist, he told me he's going to convince me that I'm, without knowing, a many-world believer. So am I a many-world believer? Why not? I mean, I think the ontology is not determined by the physics, right? I mean, this is very general. If you want to make a list of existing things, you're in trouble from day one, right? This is well known. Does the past exist or no? Yes, no, in some sense. Does Hamlet exist or no? Is there a prince of Denmark who had a lot of problems and ended up? Of course there is, Hamlet. So Hamlet exists. No, it doesn't exist because it's just a literary figure. Okay, do numbers exist? Does Lagrangian exist? So one can, the point I'm making is that by, you're free if you want to imagine that there is a full many-world, full immense wave function of the totality, but I think it's not useful for physics. It's not clarifying things of physics, and it's just a step like endowing. You can always enlarge your metaphysics. It's a step similar to, Simon mentioned this, David Lewis' super large ontology in which all the possible worlds exist. This is a way of dealing with modality. Okay, what does it mean possible, what does it mean necessary? So David Lewis says, well, let's assume, I believe that all the worlds exist, all the possible worlds exist. So I think the many world physicists are doing something similar. What about what has not happened in an interaction? Well, let's imagine that it exists somewhere else. Well, sure, if you want, you can imagine this. There's nothing wrong with it. But I don't think there's anything useful in it. And in fact, when Max defined the entropy, he defined the entropy per branch, not the entropy. Okay, we always have things per branch. Okay, but let's just talk about that. Let's call that physics. So the problem with many world ontology is not that it's wrong, is that is large, and more importantly, that it misses something. It misses the facts, because the facts are in the relative, are in the branching, not in the full thing. So let me come now specifically to relational quantum mechanics, what it is. First of all, I've just given the full story, but let me just put orders. First of all, read the standard words one uses in physics cleanly. So by measurement, just interpret a measurement as any interaction between two systems, a system X and a system O, such that the effect on O depend on the variable X of the system S. Okay? Particle hits a screen. What happened to the screen, maybe something is moved, depend on where the particle was. So this is a measurement. Therefore, there is a measurement, everything can be an observer. Exactly like in Max, a photon can be an observer. Every time observer is everything, anytime there's a correlation for the two systems created by some interaction. An observer is any physical system, okay? We're used to that from special relativity, right? The velocity of my hand with respect to this is 1 meter per second. So this is observer. This is not human, doesn't have a soul, doesn't have it's just something with respect to which velocity is given. So I think this is the role of the observer. And I will use information from now on more and more in the strict sense of Shannon. So no idealism, no subjectivism, no. Shannon defines information as a number of alternatives, period. Every time you have something that can be in a number of alternatives, the measure of the number of alternatives information. In fact, logarithm base 2 of n, but just for historical reason, that's what the information is. So this seems easy. I've given it easy. The world is facts. These facts happen in interaction. Where's the problem? Why anybody is interrelationalist immediately and follow me? Because of course there is a price to pay. And relational quantum mechanics is the recognition of this price to pay and sort of making it clear. So let me explain what the price is. The price is that the facts themselves, you have to take them depending on the observing system. Okay? So you cannot make an absolute list of facts for reality independent of the system, because otherwise you go in trouble, right? Because there is interference, essentially. So here is the price to pay. An observer, which can be a photon, doesn't need to be a human being, interact with the system and a fact A happens. Okay, this is the way we describe it in standard quantum mechanics. The variable x has the value A. But now this can be described quantum mechanically, of course, and this as a whole can interact with something else. Okay, this is a picture of interaction with something else. And when this is interacting with this, if it had interacted previously and it has knowledge of the state, namely something that codes what happened here in the basis of prime interaction, that's the description we give. There's just entanglement between the system O and the system S. And in particular, since there is an entanglement, there is no particular value of the variable A. Nothing has happened here. And so the fact that A has not happened. So the happening of the fact A exists and it's real, but relative to O and not relative to A prime. And there's nothing metaphysical of that. I want to say that in the same sense in which the velocity, this is the velocity 1 meter per second, which is true, is a physical fact, but relative to that. And has different velocity relative to something else. So there's nothing funny about that. So in quantum theory, distinct observer, different physical system, give different account of the same sequence of events. This is what has been observed by many people. Now, an immediate worry is, wait a minute, this means that this is a total solipsism. Every system knows about the world by interacting with the rest of the world and has its own picture of the world. Well, the answer is no, not at all, because systems communicate. Okay? So this guy here and this guy here can talk. And in particular, this guy here can measure OA and can measure A. And the structure of quantum mechanics is that, of course, you're going to find something in agreement. If he measure S and get the value A, then he will project the state here in the standard language. And if he asks, hey, what have you seen? I've seen OA. So there is a full consistency because of the tensor structure of quantum mechanics, which allow different systems to share information about the world and get objectivity and in the sense of common information about S. However, this is limited, and I think this is a key usefulness of this point of view. In situations like EPR, carefully arranged, this is exactly where is the paradoxical, where is the non-locality coming out? By assuming, there's an APR pair, I make a measurement here, assuming that that's forever, that's absolute. And the guys there make a measurement there, and that's forever, is absolute. If I take a relational perspective, I have a story from me on one side, thank you, and where I make a measurement, and with respect to me there is something, a fact here, and there's just an entanglement between the two systems. Only when in the future, when I get to talk with this guy there, a second fact happen, and I have so there's no interaction, no spooky action at a distance. If I look at the story from the other point of view, it's the same story, okay? There's a fact happening here, no fact happening there, And the correlation is between something happening here and something in the future when we are back again. So if you accept that facts are relative to observers, a lot of the puzzlement of quantum mechanics go away in this sense. This is a couple of papers on Pbr. I'm not going to do more about that. But there is something crucial here. If from the knowledge of the system that O prime may have, coming from previous interaction and from his calculation what has happened, what does it mean that a fact has happened? It means that there is a correlation. A correlation means, in the sense of Shannon, that the system O has information about S. A system having information about another one, in the sense of Shannon, means that in the space there is a physical constraint such that in the space of possible configuration of this system, there are constraints such that not all possible exist, but sort of the common space is not the Cartesian the Cartesian product of the two. So, for instance, if this can be up and this up, or this and down and this and down, then I say, because of some physical constraint, then I say that this finger has information about this finger. This is Shannon. Okay, this is exactly what is happening here. So O has information about S. That's what is written here. And this is what quantum mechanics is about, the relative information a system have about one another. So the existence of a correlation between the pointer variable implies that the pointer variable has information about X. And the existence of a correlation is a measurable probability. O prime can measure whether there is a correlation or no. Just measure both things and see if they're correlated or no. So physics is the theory of the relative information the systems have about one another. That's what it's all about. And on the basis of that, this is my original 96 paper that then has grown in various words. What I attempted to do at the time, and I sort of almost succeeded, then other people worked on that and did it better, but I don't want to insist on that because that I don't think is the core of the story, is that in fact you can start from that. You can start from two simple postulates that systems interact. There is a number of things that happen that you can list, okay? On the basis of that, you can predict the future. The information that you have from this outcome is what allows you to predict the future. The relevant information, the irrelevant information is the one which is not useful for predicting the future. The relevant information is what you call the state. You work this out, and then you start from two postulates. Then there is a maximum amount of relevant information that can be extracted from the system. I will come back probably tomorrow on that. And it is always possible to acquire new information about the system, right? You measure X, spin X, and then you measure spin Y. This information becomes irrelevant, so you have acquired new information, but the total amount of information is always the same. And from that, you can reconstruct the formalism of quantum mechanics. So a system is characterized by a set of variables, a set of questions you can ask to the system. The temporal sequence of the outcome of the result of an interaction define the state. Where is the Schrödinger equation? Well, very simple. Once you have the Hilbert space, if you assume that there is a time flowing, there is invariance and the time translation, there should be a one-parameter action representation of R, and then there is a unitary operator, so there is a Schrödinger equation. So the Schrödinger equation is not the core of the story. It's just something that tells, unitarity is not the core of the story. It's only something that tells you that there is a parameter that, with respect to which this happened. This is a slide from next talk, in fact, but I just want to anticipate it, just because some of you are not here tomorrow. The thing will become simpler in the presence of gravity, because in the presence of gravity, the gravitational field is part of the story, space-time is part of the story, so a system can be identified with a region of space-time. In fact, a system needs to be identified with a region of space-time. This means that the process is a region of space-time, the states live on the boundary, and this is what allows you to do quantum gravity, I think, without having to go to infinity, cleanly, using essentially standard quantum mechanics from this point of view. So this is just an anticipation of since I have a few minutes, let me just say something about discreteness. Because there's another aspect which I think is missing in all the discussion of quantum mechanics, which is discreteness. Let me just remind you, you all know that. This is birth of quantum mechanics. No? 1900 finite size packet, Planck. Einstein, discrete particles. Bohr, discrete energy levels. Heisenberg, table of number. Schrödinger, careful, not the Schrödinger equation as evolution. Schrödinger, the time-independent Schrödinger equation, which is a stationary, okay? So discrete stationary states. And then Dirac, I think this is the key equation of quantum mechanics, not the Schrödinger equation. Spectra. Now, not all spectra are discrete, but in some sense they are. What is discrete in quantum mechanics? I think that quantum mechanics is a step toward discreteness of nature, and quantum gravity is another step, independent, toward discreteness of nature. So what is discrete in quantum mechanics? There's a common scale of discreteness, right, which is given by the Planck scale, obviously. What's a Planck scale? It's an action. What is an action? Here is an action. I need a pendulum. Here's a pendulum. Okay. So this oscillates, and I make a measurement. I measure 20 centimeters the oscillation, okay, plus or minus 2. So the amplitude is the ratio of the energy, so I measure the energy. I've measured the energy is between a minimum and a maximum. So what is it that I still don't know about the system? Information. There are many possible ways this can move. There are many possible states of motion that are compatible with my measurement. I know how to characterize them. They are the region of phase space which are between energy E1 and E2. How many they are? Well, just the area of this region. The area of this region, anybody can do this calculation, is this thing here. But wait a moment. The world is quantum mechanical. Ah, yeah, I forgot. So, in fact, the energy spectrum is discrete. So how many possible orthogonal states there are compatible with my measurement? Oh, well, this is a spectrum of the energy. Anybody know how to do this calculation? This is a number. So there's a discrete number of alternative. Number of alternative, how do I measure it? Information. That's what is, okay? So there is a discrete information. There is an information which is missing when I do this measurement of the amplitude, which is finite, okay? And which is exactly A divided by H. So what is quantum mechanics telling me? Quantum mechanics is telling me that every region of phase space in fact contains less information that is apparently infinity quantity measured by energy, by action, and that there is a unit of information which is 1 h bar of action. So quantum mechanics tells me that I can translate action into information cleanly, and it has a clean geometry. This is completely general. I did it for harmonic oscillator, but of course any system with any number of degrees of freedom is the same. So the amount of information which is in a finite region of space-time per any system, it's finite in a finite region of space-time. It's a finite number, and the scale of it is given by h. And that's the first postulate of relational quantum mechanics, right? The finiteness of the information that contains a system. The same is true in quantum field theory. So discreteness, I think, is a defining property of quantum mechanics. It's the core of quantum mechanics. The scale is given by h. This is what I just said. Quantum discreteness implies that information is never sharper than h bar. So information in nature is discrete. It's not an obvious fact, because it's not measured by action. It's discrete. So it's not a tautology, this one. It's a true fact. It's a fact of nature. And so I can better use h bar as my unit of action. Is like the speed of light, right? It's once I have a preferred velocity, I can just adapt. I can take c equal 1, I can take h equal 1. It's the same story. There is a maximum velocity. Here there is a minimum amount of information in a system. So what is quantum mechanics? I think that quantum mechanics is a physical discovery of the existence of a physical limit in information transfer processes. Thanks. And I think that an interpretation that is blind to discreteness is just missing something about quantum mechanics. It's missing something core about quantum mechanics. So it's time to close. I have two final slides just to go back to cosmology. Again, tomorrow I will bring gravity in. This will be much more concrete. I will be much more physics and less foundational. And I will tell how this point of view is useful for doing quantum gravity. In fact, I think it's the only one we can do quantum gravity, unless we go to asymptotic to infinity, which is nonsense for a relativist. And I will show how it's useful in cosmology, and in fact how it's been used in cosmology by others, not by me, to go to give descriptions about early cosmology, the physics of early cosmology, of course, tentative description of physics of early cosmology, and do predictions. So let me close by the relevance for cosmology. First of all, let me repeat. Cosmology describes real facts, nothing idealistic, about a few large-scale degrees of freedom of the world and the way they affect all the rest, which is the majority of the degrees of freedom, including us, our telescope, and everything else. The observer in cosmology is totally unproblematic. Is not part of the degrees of freedom. I'm an observer, you're an observer, classical world observers. There's nothing idealistic, nothing Wigner, nothing consciousness of that. It's just a standard observer. It's just the object whose dynamic is affected by the large-scale degrees of the universe, and so on and so forth. And the dynamic of this large-scale degrees of freedom is semi-classical most of the time, but is influenced by quantum corrections, of course, in some regimes, early universe typically. In those regimes, I have to use quantum mechanics because space-time will be, in fact, I will have to use quantum gravity because space-time is not defined. So I will have to compute the way this non-space-time region affects the rest. Okay? And this will be possible to do with, if you have a theory of quantum gravity, of course. So I don't think there is any problem about foundation of quantum mechanics that touches cosmology, nor there is any problem about cosmology that touches the foundation of quantum mechanics. Perhaps inflation helps us to understand entropy. If I understand it better, I will be happy. This will be perfectly fine. I'm not saying that the two things cannot be useful for one another. This is about cosmology. What about tautology? Because I said there's a legitimate problem, which is tautology. Well, quantum tautology, again, is a problem in the philosophy and in the foundation of quantum mechanics, a legitimate problem with nothing to do with physical cosmology, is the description of the manner in which the totality of the existence of physically things interact, producing real events. So therefore, the problem of quantum tautology splits in two parts. One is how one part interacts with another one, and I've just told you this is quantum mechanics. Quantum mechanics tells how things interact with another one, okay? The velocity of this is relative to the velocity of that. So this fact is relative to this fact here. The other part, which people may legitimately ask, is how the whole interacts with something outside it, right? What is the velocity of the entire universe of everything with respect to nothing? I think that the interaction of the whole with something else is something non-existing because there's no something else. So I don't think there's any problem here either. Thank you.